So, hello everyone. Is my voice audible?
It's better.
Let us start the assignment for week number 11. So the first question here: for a millimeter wave MIMO system, the noise vector W is sampled from additive white Gaussian noise process. And the question is the noise distribution after multiplying with the RF recorder in the receiver side. So, what would be the distribution of the noise after multiplying with the RF recorder? RF recorder in the sense WRFT. In the receiver side, it is like RF recorder is for the equalizer part of the thing. So, just derive, save. This is the first question. So, there is a signal S, and it at first goes to these blocks. W, B, B, T. This is the baseband recorder. Now it comes the RF in the transmitter side, and then we transmit it in the wireless medium, and in the receiver side what it does, it takes all the signals, and then it uses the RF equalizer here, WRF R, and then it goes like WBB. This effect. So if I think what is the signal here is R, this R is equal to WRF R, this is the first part, and then what is the actual signal? And that is noise. So this noise, they have said, this is additive white Gaussian noise. Now the question is being asked here is, after multiplying with the RF decoder, what will be the distribution of the noise? So if we do such kind of thing, it becomes, what is the noise there? Actual noise after multiplying with the RF decoder into 3. Now we remember this RF decoder, this is sort of phase shift, and this noise is AWGN, and it has a special property, it is circular symmetric. So multiplying with a phase shifter here, it just add a phase term e to the power I theta, and this theta is the phase shifter terms of the phase. So it is like e to the power I theta is getting multiplied with the additive white Gaussian noise, and that is V, and it has the circular symmetric property, and this theta is constant here. Theta is not a random variable for a particular instance, like even if theta changes for different atmospheric events, for a particular thing the phase shifter provides a constant phase. So this is well known fact that if we multiply a circular symmetric noise with some random phase e to the I theta, its distribution does not change. So even if we multiply it with e to the power I theta, it will remain as a Gaussian noise. So the correct option is option B for this. Now let us go to the second question, and the second question is, in a millimeter wave MIMO FDM system, the CFO is modeled between digital precoder and RF precoder. So this is a well known question. So CFO is what? CFO. So whenever CFO is just getting added, it is added just after the demodulation part. So what we actually do the demodulation, we know in the RF side, and from RF if we do the demodulation we go to the baseband part. So this is the place where the CFO will be getting added. What is CFO? Because this carrier frequency, there will be some phase offset, and that phase offset will add some complex number e to the power j epsilon, and this will get added in the baseband. And we know in the baseband what is the signal? Signal is complex in nature, and if there is a carrier frequency offset, this will give a small complex number with small magnitude probably, and this will be getting added with the complex number. So this is what CFO does. So CFO is just added between RF part and baseband part. So it should be in the receiver side first of all, because in the transmitter side there would not be any CFO. So receiver side, and in the receiver side there is a RF part, and in the receiver side there is a baseband part. In between these two parts, this CFO will get added. So the right option is here, it should be option D, RF equalizer and digital baseband equalizer. So option D, RF equalizer that is WRFR and baseband equalizer. WBB R. This is option D for the second question. Let us go to the third question. The third question says, for a millimeter wave MIMO FDM system, how the CFO is getting added? So it is defined for all data stream in a particular time instant for a particular data stream for the whole FDM symbol duration. Option B is same for all data stream in particular time instant. and also same for particular data stream for the whole FDM symbol duration. Option C is defined for all data stream in a particular time instant, and also defined for a particular data stream for a whole FDM symbol duration. And option D is same for all data stream in a particular time instant and defined for particular data stream for whole FDM symbol duration. So if there is a CFO, how does it affect? So the relationship between CFO and a particular FDM symbol is it getting added by e to the power j, epsilon and n. Now epsilon is the phase offset, sort of the phase you can define it as the coefficient of this that is generating this CFO. It's a constant sort of thing, and n is the number of FDM samples in a particular FDM symbol. So this n is from 0 to n minus 1. So if I say n is what? N is something in 2 to the power n terms, so that we can do the FFT. So suppose this is the first string, this is the second string, this is the third string. In this way it is going. So if we sample at a particular instant here, all these data streams for a particular instance will have the same amount of CFO, but like at this point and at this point CFO will be same, but at this point and this point A and B and C, this is the time domain and this is the spatial domain. So at A and C, the effect of the CFO will remain same. However, if we move in the time domain here, then A and B will not have the same CFO, because the CFO varies e to the power j epsilon n and depends on n. So that is the reason it is same for all data stream in a particular time instant. Means for a particular time instant, all the spatial data stream will have the same CFO, and a different for particular data stream different for a particular data stream, in the sense, if I think for these data stream, if I think for these data stream, for different time instance, the CFO will be different because this n is varying here. So that is the reason option D is the correct one. So correct option is option D. Let us go to the question number 4. Question number 4 says, what is the determinant of a 16 cross 16 FFT matrix? So 16 cross 16 FFT matrix, the first property of a FFT matrix is it does not change the power of input vector. I will say this is not the power, this is sort of norm of the input vector and the output vector. So you have a vector x and it goes through a FFT matrix and the output is y. So why so? So what FFT matrix does? This FFT matrix says this is just a Fourier transform. And if we know what is Fourier transform, it takes a time domain sequence and it converts into a frequency domain representation of the same signal. So the FFT also does the same thing, and in the same time we know there is a theorem, that Parseval theorem. This Parseval theorem says just doing a FFT Fourier transform for this case it remains constant. For dt and for df minus infinite to infinite. So actually this FFT matrix has no power, and that signifies that its eigenvalues does not amplify the signal. So that is the reason its determinants are always 1 for FFT matrix. So determinant, it is the multiplication of the eigenvalues E1 dot dot dot. There are 16 cross 16 matrix, so there will be 16 eigenvalues, and multiplication of all these eigenvalues will become 1. Why? Because there is also another theorem, like FFT matrix is a unitary matrix and this matrix has a determinant of 1, or that is the reason. So the determinant of a FFT matrix is 16 cross 16 FFT matrix is 1. So the correct option is option B. For this one. So the next question, question number 5. Question number 5 says, with the assumption digital decoder matrix in transmitter side and digital equalizer matrix in the receiver side is unitary, the capacity of the channel depends on what? So first we will derive the model once, and then we will derive the cost function here, and depending on that we can define on what it depends. So let us draw that thing once again. There is something S, that is input, and this goes WPP T, and it goes WRF, and this is the wireless medium there, and I receive this signal. And this is WRF side, equalizer at the receiver side at RF part, and then it is WBB, and it goes aside. So for question number 5, we always can model a channel as y is equal to h x plus w. So what is x here? The x here is, let me write, x here is S, and H is a big matrix which includes all the terms, this wireless channel medium and all these things. So H here is WBB R first, then it WRFR, and then the wireless channel, and then the RF decoder and baseband decoder. So this is what H is. And now it is asked in the question, so channel capacity. So what will be the channel capacity in this case? So channel capacity formula is like log 2 1 plus SNR, and as I taught in the class, it becomes, for if this is a matrix, this becomes log of determinant of identity matrix. This is the equivalence of 1 plus SNR, this identity matrix, plus I have to write what is SNR. SNR means what is the power by the noise power. So there will be inverse term, and this inverse term is the RWW, and there will also be a channel, this H hat. So H hat star, this is the effect of the channel, and there will be another power of this signal, so probably that is sigma x square. So this is the term that signifies this is the actual constellation power, and after it goes through the channel, this power decreases. So this is the term which is equivalent to sigma h square, and this is the term what denotes what is the power of the noise here. In this case, it is like there is a noise plus noise B, so this could be expected value of WW star. So in this case, it is said that for question number 5, this WRF, the digital decoder matrix in the transmitter side. Let us go back to the question. The digital decoder matrix in the transmitter side and digital equalizer matrix, both of these matrices are unitary. So which are between all these things, which are unitary matrix? So first unitary matrix is the digital decoder matrix. So if that is the digital decoder matrix is unitary, that means this unitary, this is unitary, and if the equalizer matrix is also, then the equalizer matrix is this at the receiver side, this is also unitary. And if these are unitary, so this determinant is already does not matter, because they are unitary, the determinant will be always 1. So on what it will depend right now? It will depend on this WRF term at transmitter side, and obviously what is the environmental effect of the wellness channel. So the first thing is the equalizer at the RF side, and the decoder at the transmitter side, and the channel matrix H. So the correct option will be option D. Option D says wireless channel, RF decoder and RF equalizer. Now This is the question number 6. So with the previous assumption, it says that I can define the channel between digital precoder and digital equalizer as HEQ, and this channel has a SBT VE U star. So what is my video still stuck?
Now it is fine, sir. Previously it was.
Okay. So for the 6th question, the 6th question says, what is the H equivalent here from this? They said this part is the H equivalent part, and this H equivalent has a SVD of V, E and U star. So, and then this WBBT and WBR is already there. So what should be the WBB that will help me to hello, yes,
Sir, could you please show fifth question again, sir?
okay. 5th question, this is the 5th question. So it says that with the assumption, you want the answer or the question?
Thank you, sir.
Okay. So let us go back. This HEQ, this is the part of this is the HEQ part, and I have said what should be the digital precoder. So if the digital precoder is U, then what happens? HEQ into U, it will be VE, and then we can say that WBBR is equal to V star, and it becomes, V star HEQ U, this should be E. So this is the trick we play. So for question number 6, the correct option should be what here? It should be U, because it has the distribution VE. Sorry, it has the SBD VE U star. So I need a U here exactly, so that it does cancel out the effect of the unitary channel U star of HEQ. So the correct option is option A. So let us go to the question number 7, and the question number 7 says the reason of putting RF precoder in optimization framework is. So here for question number 7, it is said RF precoder in the optimization framework. Why? So this is the RF precoder here, this is the WRFT, this is the RF precoder. What is the RF recorder? This WRFT. RF recorder. So The first thing is we don't know what should be our RF decoder. So if we do not take the RF decoder in the optimization framework, then we have to initiate this from a random value, and the option number A is correct, because the cost function may not be convex, and at that time we cannot maximize the capacity in this case. And option B is also correct, because if there is a presence of noise, that can give me the wrong estimation of the angle of departure. This is also correct. And option C is presence of multiple reflectors may create the channel estimation problem tougher. So all of these reasons are correct, and these are the reasons we are putting RF decoder, that is actually helping us in beam steering and all these things that we have discussed earlier. So the correct option is option D for question number 7. So question number 8 says we have to say what is the Bayesian estimation and non-Bayesian framework. So to answer this question, the MAC says MAC is just sort of mean squared error estimation. So what does mean squared error estimation takes? So there is a term mean and square error. So what is mean squared error here? So this is question number 8. Question number 7 in question. Yeah, this is question, this has all these options A, B, C are correct, right? So question number 7 should have the right option is option D for question number 7. So what's the query here? Okay, so if we don't know what is the RF decoder exactly is, in the receiver side we may not know what is the exact value of the RF decoder, because RF decoder is in the transmitter side. So if we do some sort of cost function optimization sort of problem, at that case we have to start the optimization problem from an initial point. And how you will take the initial point, like you have to take the first point and you have to move to the solution, and each time your cost function should be minimized, like your cost function is minimizing, that's why your optimization problem is good. Like a distance, you have 2 points like here. So suppose I have this point, and from the whole space I have to reach to this point. So I have to initialize from a particular point, right? And how do I initialize that point? So I will take a random point. So this is the target point, and I have to initialize this optimization framework from a particular and any random point. It can be here, it can be here, and then I have to go update the position of the particle in this way, and at a particular time it will reach at the target solution. But for the initial value I have to start from a particular position, and this is random here. So whenever we are doing some sort of optimization problem, we have to start from initial point, and this initial point is always random. Like if you know what is the exact solution, then the optimization problem does not have any value, like you know what is the solution. So that is the we have to initialize from a random value. So that is the thing here in question number 7. We have to initiate from some random value of the RF decoder, and then we have to optimize in each step, like from suppose the cost function, that is log to 1 plus SNR, 1 plus SNR, we have to maximize this, right? So we have to check for a particular, so RF decoder has some dependency of this on this SNR. So we have to define a particular initial value of this RF decoder, that is here, and then we check what is the value of SNR, and after that we just update WRF plus some epsilon and WRF tick, and then we check what is the cost value of this cost function log to 1 plus SMR. So if we see that the capacity increases, then we keep this point. If we see the whole capacity decreases, we say like this is not an exact part. Like if this goes in this point, the distance of between these 2 points just does not decrease, it increases. So that is the count. In that way you can think. So for each WRF and its updated value, your cost function will be modified. So I have to increase the capacity here. So to do this optimization problem, at the first we have to start from an initial point, and then we have to update, and at some point we will see that our capacity has been maximized, and at that time we just drop the optimization algorithm. So that is the reason we have to start from some random initial point. So that means what? That is the random initial point here. Initiating with some random value of the digital people.
Sir, it's may not optimal. It means we are talking about the local solution, like it's not a global solution, huh?
Yes, but it does not matter here. There are a lot of algorithms. Like if we are thinking from this point, like this can happen. If there is this sort of thing, so I will go to this minima, or if I am finding the minima, and then I will see the maximum is increasing again. So I will decide that probably this is the minima. So probably this is the function. So our minima will start here, right?
But if the problem is convex, in that case,
may not be
we
convex.
should get only one minima, no?
If it is convex, then it guarantees that it will have a single minima. If it is convex, what is the function? If it is convex, the function is like this.
So if it is not written here, that means it is non-convex.
It may be. That is the problem. Like if it's not also convex, there are optimization values, optimization techniques. Like that does not guarantee that you will achieve the minimum, but there are solutions that probabilistic algorithm or stochastic algorithms that says that you will get some sort of minima, and most of the time that converges to this minima. So those are the heuristic search algorithm. Like one simple short example, I say that you search over all the domain, under all the domains, on all these domains of the function, for all the values of x, and just store all the minimum values, right? Or there could be another algorithm, like you just divide this in these small clusters, and you search over this cluster, 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 and for each cluster you will get a minimum. So if you get all the minimums, then do a minimum search over all these minimums. So even if it is not convex, for any optimization problem, you want to optimize a particular cost function, so you have to initialize the algorithm. If you do not initialize the algorithm, you cannot start the optimization technique. Like for this case, you have to take the clusters, but for each cluster there will be a WRF value, even if it is not a convex function. So whether it is convex or not convex, if you want to do some sort of optimization algorithm, you have to initialize the input for a particular value, like that should be random. The initial value of the input should be random, and then you optimize the problem and you get the particular, you get your solution. If it is convex, you will get a particular minima. If it is not convex, you will not get, probably you may not get, you may get, that depends on your luck.
So if we divide in these clusters like that, in that case computational complexity will increase now. So better is just to prove that as convex, after that we can
No,
proceed.
it is not convex, you cannot prove it convex. Sometimes you cannot prove this. This is the big task. Like if you are seeing in the two-dimensional field, it is easier to see. But there could be function. For this time, for our cost function C, This is a matrix.
This approach is also used when we are not
This
able
sort
to
of
prove that convex.
yeah, you can say, but most of the time you cannot prove that the function is convex, or maybe the
Yes.
function is not convex. Then what you will do? You will not do any optimization. You have to do some sort of optimization, right?
Yes, sir.
So that is the thing. Like probably if it is convex, you are lucky one. Most of the cases may not be it is convex. If you are finding a convex solution, then your solution is well proved. But if it is not convex, you have to say, you have to prove in somehow, or you have to show some analysis that it attains at least a close value to the minima, that sort of thing. So this is one algorithm. Like if you take all the clusters, but probably if you say about computational complexity, I will say you can improve the computational complexity in terms of time. But if you say that computational complexity in terms of hardware requirement on this or the space complexity, it increases. Like I can do the I can derive it in 4 chunks, and I have 4 parallel machines. So optimization will be more faster. Like if I do a parallel computing, like I am finding the minimum over here, minimum over here, minimum over here, minimum over here, and I have enough machine, 4 different machines. So on 4 different machines, I just do a search on a short place, a small region like this. So that will give me an advantage over time complexity. But I am here using 4 different machines, so that is the computational complexity increases there. Is it clear?
Yes, so that means we are dividing in a particular clusters like that. We are providing the random value itself. It is
And for
deciding
each
now.
of
So
them
we are
you have
moving to
to do
different
a
clusters.
optimization, and each of them starts from a random value.
Yes. Thank you.
So question number 8. Question number 8 says which of MSc, LMMSc and least square solution, what is the Bayesian framework and non-Bayesian framework? So actually what Bayesian framework does, Bayesian framework says I have some prior knowledge of my optimization, like suppose you have y and hx, but there is a noise. Now you don't know what is the actual value of actual statistics of this noise. Okay, so what you get like you get hx, the value that is exactly, and that is y plus w. So we can minimize y minus hx if we know what is the h. There could be this case. We know what is h. You can think of channel estimation and all other type of things, all other engineering technologies. This square is very common. So this is so if I want to minimize, I want to find what is my x, I can minimize over x, and I can find a particular x for which this distance is minimized. What is the distance? This is the distance, norm 2. So I am minimizing this distance over norm 2 over all the x's, and if it is a linear form y hx, then the solution is the pseudo inverse. So that is the advantage of doing the least square. Like we do not need to do all the search, we just need to do a matrix inversion. So that reduces the complexity in a lot of terms. But sometimes this may not be a linear function, like it can be a non-linear function, f of x, and this f is not hx. This can be a non-linear function like x square plus x5 plus x6, all these terms comes. So this is the case where least square actually fails. So least square fails in the sense like you don't have knowledge of first of all this W. So you are not considering what is your W. If W is Gaussian, then it works well. But if W is not Gaussian, in some case, it can be exponential distribution. Like suppose you have a signal in the constellation space. Suppose, for this case, suppose you have this and you have this. So this is a BTSK signal. Suppose this is +1 and this is -1. So I say it is Gaussian. Gaussian means it is symmetric about this. And as it is symmetric, we can think how much is the distance in terms of distance. Like if I receive a signal y here, if the y is here, we can just think what is the distance in terms of this. But probably if the signal is not Gaussian, sorry, the noise is not Gaussian, then the distribution may be like, I suppose, exponential, like this, increasing. And sorry, it cannot be increasing. It may be like this type of distribution. This is not symmetric. So in this sort of thing, we cannot say that this is the right or this will give me the best result. Here it is symmetric about all these things. So we can think of in the terms of distance. Because why? Because Gaussian has the thing like y minus h, sorry, suppose you have a Gaussian distribution. So it has like, if the so suppose the mean is mu and variance is sigma square. So Gaussian has this sort of distribution. So this itself is a norm 2 factor, but for exponential it is like e to the power minus x. So that is the reason Gaussian may give you a better estimate for LS sort of thing. But if the noise comes from exponential distribution, LS will not give you the best result, because this norm 2 will not work. Norm 2 works because Gaussian has this sort of square term there, but for exponential there is no square term. So that is the reason most of the time we take the expected value of the error and then we minimize it. So this is what MAC is. But for this you have to know what is the statistics of this W. And also here we are taking Hx. So we say here that what is the estimate of y, that is a linear function of x. Why linear? Because I am multiplying h with x, but probably f of x, and this is not linear. In that sense it is also MAC. So that MAC is minimizing y minus f of x. F can be any function, and linear MAC is if I take f is a linear function, that is hx. So in MAC or LMMAC we take the statistics of the noise and statistics of the input signal also, x or y. So we have the information about both of them, but for least square we do not take any statistics. So that is the reason least square, as it does not take any prior knowledge or prior knowledge on statistics of the signal model. So that is why LS method is not a Bayesian method. But MAC and LMMAC, they both take the statistics of the noise, and sometimes LMMAC takes the statistics of the input signal like covariance matrix of X and all these things, or you can say the cross covariance matrix of y and x, these terms LMSE needs. So this needs the statistics. That's why the correct option will be option B. MSE and LMMSE both are Bayesian estimation procedure. So let us go to the question number 9. Which of the following is design parameter in transmitter side? So see, channel gain and angle of aperture are not the design parameters. These are the things that depends on the environment. So there are two things here that are design parameters: baseband equalizer and beam steering. But this beam steering is in the transmitter side and baseband equalizer in the RF side. So that is the reason here only it is asked what is the design parameter in the transmitter side. So correct option is option D, and it is the beam steering. And the last question is, for capacity optimization problem, the multiplication of digital precoder and RF precoder matrix is matrix U. If the L2 norm of the matrix U is 1, so it says the multiplication of digital precoder matrix and RF precoder matrix is U, and this has the L2 norm of matrix 1. So the optimization of design parameter lies in which side? So let us write that equation once more. So it was like it depends on that big H matrix is WBBR, WRFR, and then it comes H, WRFT, WBBT, and S, plus some noise. This is the Gaussian noise of the channel, and it says that for our case, this is the data model. Let us write what is the H here: WBBR, WRFR, H, WRFT, and WBBT. So they have said in the question that the multiplication of digital precoder and RF precoder matrix is U. So this is the part U, and this is the unitary matrix. So this does not affect my cost function because determinant of unitary matrix is the identity matrix. So what left out here? WRFT and WBBT. And in which side they are? They are in the transmitter side. So sorry, so probably the option was given as it was wrong. So sorry, it is in the, sorry, it should be receiver inside. Sorry, I have made a mistake here. They have said that this part is unitary matrix, as the question suggests. Question suggests that digital precoder and RF precoder. So this is the digital precoder, WBBT, and this is the RF precoder. So this part is the unitary. So the cost function depends on this part, and let me remove this part. This part depends on, the cost function depends on this part only, and this is in the receiver side. So that is the reason the correct option will be in the receiver side. The correct option is A. So any more doubt from this session?
Yes, sir. In question 5 solution,
Okay. Question 5 solution. Yes.
act- actually that is not exactly related to question 5 solution, but in that we use that RWW inverse, that matrix, covariance matrix. So during the lectures, that particular matrix is dropped actually during the optimization framework. So why this matrix is dropped? Actually, I couldn't get that point.
Dropped in the sense.
It is not considered for further writing expressions. It is not seen
Okay. See,
actually during the
the
lectures.
you cannot probably this is not a design parameter that RWW inverse. Okay. Why not? That is a design parameter. You cannot take it in the optimization. Like you cannot control the noise, right, in the receiver side.
So we have to calculate it and put that
So
value
you only
like
have
that.
the statistics of that. You will never get what is the actual noise. So only that noise statistics is known to you, nothing more than that. So you have no control over that. So you cannot change what is the noise according to you. Noise will also
Yes.
be will always be there. So you have to take the statistics, not the actual value. Suppose the noise is Gaussian, so and it is uncorrelated. What will be in that case? The diagonal elements will be there, and the diagonal elements will not be there. If I take the expected value, covariance matrix. So they have not taken it in consider because that is not a design parameter. What is design parameter? What you can control. You can control the RF
Mm.
recorder, baseband recorder, all these things is in your control. So your optimization should be on all these parameters that is under your control, not on the which like channel you cannot control, the wireless channel actually. So that H matrix you do not take anymore, and also the noise is V, and that V you cannot take control of. So H and V you cannot change according to you. You can only change the precoder and equalizer, all these things according to you, so that you can counter the effect of H and V. That is the concept of the wireless medium. So that is the reason that RVV that is likely you, it is known to you, the statistics is known to you only, and it does not change.
So we will not put it in mathematical expressions, all that.
You put it, but you cannot calculate on it, like you do not optimize on it. Like, suppose you have a function y is equal to ax, a is a constant, then if you optimize
So we
this
can
problem,
ignore that in cost function, na? That
you can,
means.
you should take it in the cost function, but you cannot change it. Like I say y is equal to 5x, so you cannot change the term 5, right?
Yeah, then understood.
That is the thing, only noise you cannot change in this case. So that is the reason you take it as a constant here for
Yes,
optimization
sir.
terms.
Yes,
Okay,
sir.
thank
One more small doubt, sir. Actually, we do this SVD decomposition.
you. Yes.
Sometimes we do that eigenvalue decomposition,
Okay.
and sometimes we also do that Cholesky decomposition, LU decomposition.
Okay.
So, what is the situation in that we use these three decomposition?
Okay. So can you see SVD exists for most of the matrices. Like there is a matrix U, there is a eigen matrix, that is not a eigen matrix, that is singular matrix epsilon, and there is another interior matrix V. So if the matrix is rank efficient, the SVD always exists, but EVD does not exist for some cases. So what is EVD? EVD always gives you U, E, U star, and let me write.
So, based on the rank, we decided
Uh,
whether we go for the SVD or EVD.
uh, Not exactly, like if you see, the main thing here is let me calm the screen. So there is H and it has U epsilon B star. So this H probably have a M cross N matrix. So to do that, it will have a M cross N matrix, M cross N matrix, and M cross N, and suppose, so that this rank matches. Suppose H has, sorry, I have to do it more. And there should be two unitary matrices, and these matrices are always common. So this should be a, let me once do it. Okay, so this suppose this is a m cross m matrix, and this is a n cross n matrix, and these diagonal elements will be m cross n. If I do in this sort, the diagonal elements, it depends on m cross n. So SPD, what it says, it is singular value. It is only for rank efficient matrices. But suppose H is a normal matrix and it is also a full rank matrix. If such is the case, we can have this sort of similar decomposition, that is U sigma U star. Okay. So a common application I can say, like see, H is a matrix that is m cross n matrix. So let me derive why this SVD and EVD comes like that. So suppose H is a m cross n matrix and it has a decomposition U epsilon V star, and H star should be n cross m matrix, right? So what will be V star? Sorry, it should be V epsilon star into U star. If I multiply H star, it becomes m cross m matrix, right? Because this is m cross n and this is m cross m. So this is m cross m matrix and it becomes V epsilon star U star U epsilon V star. This term cancels out and it becomes epsilon star epsilon and V star. So this is what in this case EVD exists. Why EVD exists? Because this is a m cross m matrix. So if it is a full rank matrix, this EVD exists, but it is not a full rank matrix, a n cross n. So in this case SVD exists. And if you say what is the LU decomposition, suppose there is a matrix, so that matrix can be divided into lower triangular and upper triangular form. So the first matrix is lower triangular and the second matrix is upper triangular. You can have this decomposition. So that is what LU decomposition is. And if you say what is the keyword decomposition, so keyword decomposition is sort of it comes from sort of this SVD, you can say. So how can I derive the keyword decomposition from the same SVD or EVD? So keyword decomposition, this is, suppose what I said, there is a EVD decomposition of a matrix H or SVD, you can think. So take it EVD, so U epsilon U star, or it is SVD, then U epsilon V star. Now you take this U term are like you just cut this term out. So I say this term is R and this is Q. So a matrix has a decomposition of Q, which is the unitary matrix U here, and the part R, that is the part epsilon V star. Okay, so the thing happens, this R becomes a upper triangular matrix because this epsilon is a diagonal matrix. So this is another sort of decomposition. So all the decomposition comes from the same matrix. You can represent the same matrix as SVD, keyword and LA. So it depends on you how you want to in what decomposition you are getting the advantage for the P-coding. Is it clear now, or something is missing?
Yes, sir. Thank you, sir.